After studying this module, you shall be able to learn the basic assumptions of Walsh rule, understand the Walsh diagram, predict molecular geometries using the basic theoretical assumptions and Walsh diagram, analyze the effect of change of molecular orbital energies with bond angles, know the application of Walsh diagram for predicting the geometrical shapes of molecules through the correlation diagrams of their orbital energy, explore the application of Walsh diagram for determining the structure of triatomic molecules. Many theoretical models have been developed to understand the geometrical arrangements of molecules or the shapes adopted by polyatomic molecules in their ground as well as in their excited states. A. D. Walsh in 1953 gave correlation diagrams which were plotted for the orbitals of linear and non-linear triatomic molecules. These diagrams are named after A. D. Walsh, a chemistry professor at the University of Dundee. Walsh diagrams are also called as angular coordinate diagrams or correlation diagrams. He applied theoretical contributions made by Mulliken to calculate and explain the effect of changes in the geometry of a molecule with the change in the energy of molecular orbitals. It has been used to predict the geometrical trends in a qualitative or semi-quantitative manner. Walsh diagrams track the energy of molecular orbitals as the shape of the molecule is changed. The shapes adopted by polyatomic molecules could now be successfully rationalized in both the ground as well as in the excited states. Walsh diagrams gives the electronic orbitals, shapes and spectra of polyatomic molecules, particularly the non-hydride triatomic molecules like AB2. The salient feature of this stereochemical model or the justification for this simple theory is determined to a very great extent simply by the number of valence electrons in a given system. It is important to note that a molecule will adopt a structure that provides the stability for its highest occupied molecular orbital, that is HOMO. Walsh rule. According to Walsh, the following facts are generally true regarding the shape of the molecules. The molecules with 16 valency electrons are linear in their ground states. Molecules with 17 to 20 valency electrons are bent in their ground states, the apex angle decreasing markedly from 16 to 17 and then from 17 to 18 electron molecules and less markedly from 18 to 19 and from 19 to 20 electron molecules. Molecules with 22 electron are linear or nearly linear in their ground states. The Walsh diagrams are illustrations of the dependency of the variation of angles on the energy of the molecular orbitals. The conclusions are known as Walsh rules. Based on the pioneer work of Walsh, Gimac has specified the following assumptions for the application of qualitative molecular orbital theory. These are: electrons are completely delocalized in molecules. Further, they move in molecular orbitals extending over the entire molecular framework. Only the valence electrons should be considered for properties, which can be explained by the qualitative molecular orbital theory. the linear combinations of atomic orbitals can form satisfactory the molecular orbitals. The molecular orbitals for each type of molecular framework must be qualitatively similar. The individual molecules may differ only in the number of valence electrons occupying the common molecular orbital system. The total energy of the molecule is the sum of the orbital energies of the valence electrons. The electron-electron or the nuclear-nuclear repulsions are not considered in this simple model. The symmetry restrictions limit that the particular atomic orbital can combine to form the molecular orbital. The molecular orbitals must be either symmetric or antisymmetric with respect to the symmetry operations of the molecule. It is possible to draw pictures of the molecular orbitals and to establish the approximate order of energies from the properties of the atomic orbitals. Then, the changes in the molecular shape accompany the lowering of the energy of the molecular orbitals, resulting from an in-phase overlap between two or more atomic orbitals. Conversely, the rise in the energy of the molecular orbital is observed when these atomic orbitals overlap in an out of phase manner. Now, let us study about these Walsh diagram. The Walsh diagram, as originally discussed by Walsh in 1953, is a plot of the change of the molecular orbital energies with the change in the angular variable or the apex angle. Let us start with Ab2 type molecule. It is assumed that the lowest energy orbitals of linear Ab2 molecules are built solely from s and p atomic orbitals. The two lone pairs of s orbitals, one on each b atom. It is assumed regarding the molecular shape that they are built up from sb hybrid valencies of A plus the p sigma valencies of the two b atoms, and these are largely localized one to each A-B distance. The spectroscopic transitions involve non-localized combinations of the localized orbitals and be labeled as sigma g and sigma u. We note here that the hybridization of the s and the p valencies of the b atoms is neglected for simplification. The in-phase overlap of a p pi atomic orbital on each of the three atoms will form a pi u orbital, and it will be bonding and two-fold degenerate. The out-of-phase overlap of a p pi atomic orbital on each of the b atoms will result in the formation of pi g orbital, which has zero amplitude at the central atom, being localized entirely on the b atoms. Further, it is two-fold degenerate, weakly BB antibonding and AB non-bonding. A pi u orbital is formed by the in-phase overlap of a p pi atomic orbital on each of the b atom, and these overlapping are out of phase with a p pi orbital on the central atom. Again, it is also two-fold degenerate, BB bonding and AB antibonding. A bar is placed over the symbol just to indicate AB antibonding nature. Now, this Walsh diagram is also given in figure. As you can see, this figure represents the empirical angular correlation diagram for a general AB2 system. The geometry of various molecules of a given family can be easily predicted on the basis of the occupancy of molecular orbitals in a particular electronic state. Generally, a bent geometry results due to the occupation of a level whose orbital energy curve decreases with diminishing internuclear angle. The opposite effect, that is, a linear nuclear arrangement, is observed for the population of a molecular orbital whose energy increases with such deformations. Thus, the AH2 or AB2 system with 4 valence electrons will be linear in their ground states due to the double occupation of all levels including the 1B2 molecular orbital, and those with 5 and 6 valence electrons such as BH2 and BH2 anion respectively are expected to prefer the bent geometries due to the occupation of 3A1 molecular orbital. The Walsh diagram for AH2 system can be redrawn as is shown in figure. Further, other classes of molecular systems can be explained in the similar manner by introducing different correlation diagrams. The Walsh diagram for AB2 system is shown in figure. Such systems possess more strongly linear ground state structures. Their aversion to the bent nuclear geometries can be ascribed to the successive population of the 1 pi, that is 4b2 1a2 pair of molecular orbitals due to the increase in the number of valence electrons from 12 to 16 respectively. However, the strongly bent tendency is exhibited by the occupation of 6A1 molecular orbital, the next most stable species. Such observations are equally valid for both ground as well as for excited states. Hence, the stereochemical changes in electronic transitions can also be understood by studying these Walsh diagrams. And this figure 3 represents the orbital overlap and the Walsh diagram for AB2 system. Now, let us study some of the applications of Walsh diagram. Walsh diagrams for AH2 molecules. Consider a molecule AH2 where the element A, this belongs to the second period of the periodic table. The molecule AH2 can either have an angular geometry with C2V symmetry or a linear geometry with D infinity H symmetry. The only orbital available with the hydrogen H atom for bonding is 1s orbital, and the symmetry adapted linear combinations of the two 1s orbitals of the hydrogen atoms which are capable of forming bonds with orbitals of atom A in both the angular and the linear geometry are psi 1s of HA plus psi 1s of HB and psi 1s of HA minus psi 1s of HP, that is additive as well as subtractive addition. These combinations are of A1 and B2 symmetry respectively. In the angular AH2 molecule and of A1G and A1U symmetry respectively in the linear AH2 molecule. Further, in the angular AH2 molecule, the two atomic orbitals of A of A1 symmetry are 2s and 2pz orbitals, and the one with B2 symmetry is the py orbital. In the linear AH2 molecule, the atomic orbital of A which is of A1G symmetry, is 2s, and the atomic orbital of A, which is of A1U symmetry, is 2py. We shall first consider bonding in angular AH2. Now, the combination Chi 1s Ha plus Chi 1s Hb, which is of A1 symmetry, combines with two mixed 2s-p-z orbital of A, also of A1 symmetry, to give three molecular orbitals 1a1, 2a1 and 3a1. The bonding 1a1 molecular orbital utilizes the mixed sp-z orbital of A having predominant 2p-z character, and the bonding 2a1 molecular orbital utilizes the mixed sp-z orbital of A having predominant 2s character in the angular AH2 molecule with HAH angle 90 degree. Now, as the bond angle increases, the participation of 2p-z orbital in the mixed sp-z orbital in 1a1 decreases, and that of 2s orbital increases, with the result that in the linear geometry of AH2, it is only the 2s orbital of A1G symmetry which combines with the combination Chi 1s Ha plus Chi 1s Hp, also of A1G symmetry, to give the bonding molecular orbital 1A1G. Since the 2pz orbital of A is of higher energy than the 2s orbital, the lesser and lesser participating of 2pz in molecular orbital 1a1 will cause a greater and greater decrease in the energy of the molecular orbital in going from the angular AH2 molecule to the linear AH2 molecule. That is, the HAH angle of 90 degree changes to the HAH angle of 180 degree. Similarly, in the 2a1 molecular orbital in the angular AH2 molecule, the contribution of 2s orbital goes on decreasing with increase in HAH, with the result that in the linear AH2 molecule with HAH angle 180 degree, there is zero contribution of 2s orbital. The contribution of the 2pz orbital, on the other hand, goes on increasing with increase in HAH angle from 90 degree to 180 degree. However, the 2pz orbital in the linear molecule is non-bonding, because in the linear molecule the Chi 2pz and the combination Chi 1s Ha plus Chi 1s Hp are of different symmetry. The decrease in the contribution of 2s orbital of A with the increase in the angle HAH in 2a1 molecular orbital is reasonable due to the increasing contribution of this orbital to the lowest energy bonding molecular orbital, that is 1a1. In the angular AH2 molecule, the 2a1 molecular orbital is of lower energy than in the linear AH2 molecule, because as can be seen from the Walsh diagram, this molecular orbital has a positive overlap with the 1s orbital of hydrogen, whereas it has no overlap in the case of linear AH2 molecule. The 3a1 molecular orbital is antibonding, and this has not been shown in the diagram. The symmetry adapted combination, that is Chi 1s Ha minus Chi 1s Hb of B2 symmetry, combines with py orbital of the same symmetry in the angular AH2 molecule to give bonding and anti-bonding molecular orbitals of the same symmetry. Only the B2 bonding orbital is shown in the Walsh diagram. It can be easily visualized that if we go on decreasing the HAH angle in the angular AH2 molecule, the overlap between psi 1s HA minus psi 1s HB and py orbital in the bonding B2 molecular orbital will go on increasing, and hence the energy of this molecular orbital will go on decreasing, with the result that B2 molecular orbital has now the lowest energy in the linear AH2 molecule, that is the angle HAH equals to 180 degree. The px orbital of A in both the angular as well as in the linear AH2 molecule is non-bonding. In fact, in the linear geometry of AH2 molecule, both the px and py orbitals are degenerate, non-bonding and are of E1U symmetry. The various orbitals which take part in molecular orbital formulation of AH2 molecules are 2s, 2px, 2py and 2pz orbitals of A and 2 1s orbitals of hydrogen atoms. Thus, 6 molecular orbitals are formed, out of which the 4 lower energy molecular orbitals are shown in figure number 3. The 4 molecular orbitals can accommodate 8 valence electrons, which is the maximum number of electrons that are present in AH2 molecule, since we know that A belongs to the second period. It follows from the Walsh diagram of AH2 molecule that a linear geometry of BeH2 would be more favorable than the angular geometry. This is because the two tilted lower energy molecular orbitals of linear geometry of BeH2 are of lesser energy than the two lower energy molecular orbitals of angular BeH2. To sum up, if there are only 4 electrons to be accommodated in the molecular orbitals of the molecule AH2, say for example BeH2, the molecule would have a lower energy linear geometry. If, however, the number of electrons to be accommodated in molecular orbitals is more than 4, for example in water, the third molecular orbital has to be occupied, which is of much lower energy in angular AH2 molecule than in the linear AH2 molecule. Now, the filling of the fourth non-bonding molecular orbital is of no consequence in determining the geometry of AH2 molecule, since this non-bonding molecular orbital is of the same energy in linear as well as in the angular geometry of AH2 molecule. In such a case, the molecule will have an angular geometry. The ammonia molecule represented as NH3. Now, here in ammonia, each of the 2s and 2pz orbitals of nitrogen is of the symmetry A in C3v point group to which the molecule belongs. The 2px and 2py orbitals taken together are of the symmetry E. The 3 1s orbitals of 3 hydrogen atoms can linearly combine with one another to give 3 combinations, one of which is of the symmetry A and the rest of the 2 combinations taken together are of the symmetry E. Now, the linear combination A of 1s atomic orbital of hydrogen combines with 2s 2p orbitals of nitrogen, each one having the symmetry A, to give an equal number of molecular orbitals. That is, we now get 3 molecular orbitals. In the same way, the two linear combinations E of 1s atomic orbital combines with px and py orbitals, also of the symmetry E, to give two sets of doubly degenerate molecular orbitals. It is possible to write the wave functions and draw the diagrams of all the 7 molecular orbitals of NH3. The electronic configuration of NH3 is sigma 1A2, sigma 2A4, sigma 3A2. The 2 electrons in the highest occupied molecular orbital, HOMO, which is almost non-bonding, are particularly localized on nitrogen atom. The remaining occupied molecular orbital are of bonding type. This simple molecular orbital description of NH3 tallies with the conventional picture of NH3 having a lone pair of electrons on nitrogen atom and 3 NH sigma bonds. But it does not explain the equivalence of the 3 NH bonds and the observed NHN angle. These are explained on the basis of Vesper theory and or the concept of hybridization as discussed in the next chapter on hybridization and shapes of the molecules. Summary. This module discusses about the following points. Walsh diagram, which is an illustration of the dependency of the variation of angles on the energy of molecular orbitals. The Walsh rule, which states that the molecular geometry is determined to a very great extent simply by the number of valence electrons in a given system. The Walsh diagram plots that helps to predict the geometrical shapes of the molecule from the variation in their bond angle with respect to the molecular orbital energies. Application of Walsh diagram for determining the structure of various molecules.